Okay, so in this chapter, we'll talk about nuclear reactors. Okay. What I'm going to do is I'm going to go all over the slides. I'm going to give you a essential picture, what is the main things in the nuclear reactor, and then we'll go over the slides. Okay. So here's the thing. In a nuclear reactor, what you are splitting is a uranium-235 isotope nucleus. Okay, so uranium-235 in the periodic table, see that's the last element in the black on the bottom row. That's the U992. So in the bottom row, 89, 90, 91, 92. Okay, so that is the heaviest element that occurs naturally. Everything after that, in the white, those are man-made. Okay, so you make them in accelerators and nuclear reactors and stuff like that. And they're not stable. So U92 is the heaviest stable naturally occurring element. And here's the deal. So if you go mine uranium, this isotope and uranium-238, what you get is a combination of these two guys. Okay, so this thing, uranium, is identified by 92 protons. Okay, so it has 92 protons and 92 electrons. So uranium-235, it's 235 minus 92, which is 135 plus 8, 143 neutrons. So this guy has 143 neutrons, and this guy has 146 neutrons. Okay. So this guy has 92 protons, 143 neutrons. This guy has 92 protons and 146 neutrons. So this guy is just a heavier cousin. In a nuclear reactor, this is the fellow that you're splitting. Okay? You're not splitting this guy. This guy can be used to make fuel. This guy can be used to make plutonium, which is plutonium-94, which can also be used in a nuclear reactor. So you guys might have heard of breeder reactors, and that's what they do. Okay, there's another one that they use as well. Okay, this is the guy you split. Okay. Now, in naturally occurring uranium, 99.2% is uranium-238. Only about 0.8% is uranium-235. All right, so in a nuclear reactor, you went on the tour, right? So to make fuel in a nuclear reactor, you have to enrich it. You want a higher percentage of uranium-235. For a bomb, you need to enrich uranium. In a bomb that explodes, you want over a 70% uranium-235. So you got to enrich it quite a bit. And that's a hard and expensive process. Okay. All right, this is what uranium-235 is what we are going to split in a nuclear reactor. Okay, so here's the process. You take a neutron and shoot it at uranium-235. This uranium-235, if it has the right energy and all that, and we'll talk about all the details, this absorbs the neutron. And then what happens? It becomes uranium-236. It becomes unstable, and then it'll split into two pieces, roughly about equal size. Well, Anyway, it'll split into two pieces, and then in addition, 3 neutrons come out.
Why is it split into two rather than just decaying to like beta or alpha?
Well, when it absorbs, there is this, because this thing, the strong force, it's tightly bound, and it releases about 8 MeV of energy, and that energy makes it split.
Oh, so instead of like just being because of the force, it wasn't in the sense of split.
Oh, it's not the force. It's when the neutron gets absorbed, there's a strong binding force, and you can think of it as now the neutron has become lighter, and that missing mass, that energy splits that nucleus. All right, so you take this guy, hit uranium-235, he absorbed the neutron, and then he split. And this is the products that were formed. 2 large pieces and 3 neutrons. Okay. You guys understand it so far? All right, so here's the deal. Everybody knows this equation, E equal to mc squared. What this tells you is, this equation tells you is the energy equivalence of mass. Okay, c is the speed of light, and the speed of light is 3 into 10 to the power 8 meters per second. 3 into 10 to the power 5 kilometers per second. If you could make light go around the earth, it would go around the earth 10 times in 1 second. That's how fast light travels. Okay. The fastest we have traveled, let's say in a space shuttle or something, is 10 kilometers a second. And this is 300,000 kilometers a second. Okay. And so this is 30,000 times faster than the fastest we've traveled. Okay. Anyway, so here's the energy equivalence of mass. Okay, so now why do we bring this up? Right, so you shot a neutron into uranium-235. Anytime you get energy, if energy is released, that means the products weigh less than the ingredients. Okay, so here, this is the mass of the ingredients, this is the mass of the products. So if you want to release energy, the mass of the products has to be less than the mass of the ingredients. What if the mass of the products is greater than the mass of the ingredients? Then you have to put energy into the reaction to make it go. Okay? All right, so we're saying that these guys weigh less than this guy. Well, what happened to the missing mass? That missing mass is what got converted to energy, according to this equation. Missing mass got converted to energy. And what? Mass of ingredients minus mass of product, C squared. So you see, if the mass of the ingredients is greater than the mass of the products, you get energy. Did you guys understand that so far? All right. Now, well, so what is the big deal about nuclear energy? Why do we like it so much? I'm sorry? What do you mean effective? All energy?
Well, no, it just produces a lot of energy.
Yes, so that's why we're, okay. So, so just to give you, so when you split one uranium-235 nuclei, you get about 200 MeV of energy. Okay? We'll come to that. MeV is a electron volt is a unit of energy, and this is a million electron volts. Okay? When you burn one carbon atom, you get energy. So you get energy. What does this mean? That the carbon dioxide weighs less than these guys. Okay? Except that the energy you get is 4 eV. So this guy is 50 million times greater than this guy. When you split a uranium nucleus, you get 50 million times more energy than when you burn one atom of carbon. And this is good. Okay, so you'll take that any day. Okay. What is the other benefit?
No CO2.
No CO2. Okay, so that's the big deal. So no CO2. Okay, so nuclear energy is great. All right, so now let's figure this out. All right, so here we split a uranium nucleus. You got 2 pieces and then 3 more neutrons. And then and you got a bunch of energy. How much energy did you get? 200 million. Okay, now you want to keep this gravy train going. Okay, now if you want to keep the train going, what you want to do is you want to make sure that one of these 3, on the average it's about 2.45, okay, that one of these 3 causes a further reaction. If none of these guys cause a reaction, then the reaction dies. Okay, you got 200 MeV and then that's it. If one of them causes a further reaction, you can keep the reaction going. You got to make sure at least only one of them causes a further reaction. And then the nuclear reactor will keep running. If less than one causes a reaction, then the reaction dies and the reactor shuts down. If 2 of them cause reaction, what will happen?
Explosion.
It will be an explosion. Okay, so you want to make sure one causes a further reaction, and that is criticality. Okay, so in a nuclear reactor, that's what you're maintaining. All right, so now you do everything to make sure that one of those causes a further reaction. Okay, good so far? All right, so now let me show you another graph. This graph shows you, okay, this fission cross section. Is that essentially this? You can think of this as the probability of a neutron causing a fission reaction in, here's uranium-235 and this is plutonium-239. Plutonium is not naturally occurring, but it's manufactured in a nuclear reactor. Okay, so well, we won't worry about that. So this is the graph we'll look. Okay, when these guys come out of a fission reaction, they're going extremely fast. They're going at about 20,000 kilometers a second. Okay, so they're going at about 1/10 the speed of light. 20,000 kilometers a second. They would go around the Earth in 1 second. Okay. All right, so here's the problem. They're going very fast. Okay. So this is MeV, the energy is in MeV, they're going about that fast. And the probability of them causing a fission in uranium-235 is about 1. But if you could slow down these neutrons to about that speed, then the probability of them causing a reaction in another uranium-235 is about 100 times greater. Okay. Remember, you're trying to get this guy to cause a further reaction, but these guys are too fast, and when they're going that fast, they don't cause a further reaction. Okay, they'll cause a reaction, but the probability is small. Now, if you could slow these guys down from 20,000 kilometers to 2 kilometers a second. Okay, so you have to slow them down from 20,000 kilometers a second to 2 kilometers a second. Then the probability of them causing a reaction greatly increases, and you can make sure it causes a reaction. Yeah. Who slows them down? So you have to have a material to slow them down, and that guy is called a moderator. Okay. So you need moderators to slow down neutrons and to make sure that the neutrons produced will cause a further reaction. Yeah. What is your biggest concern about the nuclear reactor? You don't want more than one to cause a reaction. Okay? And you need to have some way of shutting down a nuclear reactor. How do you shut down a nuclear reactor?
Think about rods, no?
Well, yeah, but what does it do? In this picture, how do you shut down a nuclear reactor?
You absorb the excess.
You absorb all these three guys, and you can stop the nuclear reaction. Okay? And that's the job of the control rod. Okay? The control rod is a neutron absorber. Yeah. All right, so those are the ingredients of a nuclear reactor. Okay, so So the components of a nuclear reactor are: you need a fuel, you need fuel. And what is your fuel? This is your fuel. You need a moderator. What is the moderator doing? Slowing down neutrons. Okay. Now here is, so let's say I have ping pong balls, and I shoot ping pong balls at, so I have a ping pong ball that I throw at 100 miles an hour at a bowling ball. Will the ping pong ball slow down? No, it just bounces off. What if I have a ping pong ball and throw it at another ping pong ball? It will slow down. So the moderators have to be light materials. Okay? They can't be heavy materials. And control rods are made of stuff that will absorb neutrons. Okay? So materials that absorb neutrons to prevent more than one neutron from causing fission. Okay? So here is the setup of a nuclear reactor. Okay? So there is the fuel rods. Okay? Here are control rods. Okay? So if you put, so there are slots between fuel. Again, this is one configuration. There are other configurations. You want to shut down the nuclear reactor, just shut down, drop the control rods. Yeah. And here is moderator. Moderator. In this case, the moderator happens to be water, and the moderator is also taking away the heat, absorbing the heat. When you produce heat, when a nucleus split, this gets hot, and when it gets, what do you do with that heat?
Boil the water.
What's that?
You boil the water.
You boil water. Why do you boil water?
Great speed
Why do you create steam?
for energy.
To turn.
Hmm?
To turn.
This is why you create steam. Okay. So here's a piece of wire between magnets, sitting between magnets. Okay. When you turn it, you produce electricity. And that's a nuclear reactor. Okay. All right, so let's, so here's a picture, another picture. Um, so these are control rods, those are fuel rods. Uh, Here's water that'll, when a nucleus is split, heat is produced, this water will get hot, turn into steam, which is going through a turbine. The turbine is what is turning that wire in the generator, okay? And then the steam is, so you build nuclear power plants near large bodies of water, okay? And you take water from the lake and cool this steam down to pass it back through the nuclear reactor. Why do you have to cool it down? So cold water can absorb more heat from there, okay? And it turns out that if 100 joules of heat is produced, 35 joules of that is converted to heat, and 65 joules of that is dumped into the river. For every $3 of heat produced, you're converting $1 to electricity, and $2 you're throwing out the window. Because that's the best you can do. Because you can't convert all of that to electricity. All right, so that's the nuclear reactor. You guys understand that? Okay. Any questions before we get into the slides? All right, so now we'll look at some of the details. All right, so we'll look at the fission process in isotopes of uranium in an isotope of uranium, and U-235 is what you split. What is critical reactions? What is criticality? When one neutron is causing another fission reaction, okay? Types of thermal fission reactors. So the way you extract heat, you classify reactors based on that. We'll talk about how many reactors there are in the world and so on. Yeah. Then we'll talk about methods of nuclear waste disposal. Nuclear reactors are one of the safest modes, things out there, but still it's, people get scared, and so, safety is what designs, you come up with new designs which are foolproof. Yeah. So they're absolutely safe. Yeah. And then we'll talk about breeder reactors. Breeder reactors produce fuel from U-238. Okay, so they'll produce plutonium, and you can also use thorium to produce fuel. Yeah. All right, so let's, since I'm recording this, all right, again, in all these reactors, in a coal power plant and all that, what you're trying to do is, here's this coil between magnets. You want to turn this coil to produce electricity. Okay, and if the setup is like that, you'll produce an AC voltage, and the heat produced when you split nuclei is used to produce steam, which turns this coil to produce electricity. So this is the device called a generator, which turns heat into electrical energy. Okay? And in a nuclear reactor, it's about 35% efficient. In a coal power plant, it's about 40% efficient. Okay. The efficiency depends on the temperature at which you're operating. Okay? So in a nuclear reactor, mass is converted to heat, and about 35% of its heat is converted to electricity. What do we mean by the mass is converted to heat? What does that mean?
When the products weigh
Way less.
less.
Yeah, yeah. Okay, so these guys weigh less, and the difference in the mass, this guy weighs more than this guy, and so the difference in mass is what's converted to heat, energy, heat. Okay. So an exothermic reaction, okay, so when energy is released in the reaction, that is called an exothermic reaction. When you need energy for the process to go through, that's an endothermic reaction. Okay, so if you need energy, then this is an endothermic reaction. This is an exothermic reaction when energy is produced. Okay, so that's an exothermic reaction. There are nuclear reactions that are endothermic. You need to put in energy for them to go forward. Okay, we are interested in an exothermic reaction, reactions that release energy. Okay, so here's a fusion reaction. This is what happens in the core of the sun, okay, for instance. And we can sort of do this on Earth as well. We'd like to do this on Earth as well. Here's a fusion reaction. This is deuterium, which is a proton plus a neutron. So this is a heavy hydrogen. Okay? And here's tritium, again, another isotope of hydrogen. Okay? 1 proton and 2 neutrons. You can combine these to form a helium nucleus, okay, and a neutron. Okay? So these are the products, these are the ingredients. This guy weighs less than these guys, and energy is released. So this is a fusion reaction. In a fusion reaction, you're taking light nuclei and combining them to a heavier nucleus. In a fission reaction, you're taking a heavy nucleus and splitting it. Okay. We'd like to be able to do this. Why do we want to do this instead of that? This is old technology. This is the energy released is roughly the same. We've been trying to do this for a while. Why do we want to do this? We've already mastered this technology.
Oh, things like the radioactive waste.
That's right. Okay, this stuff, these pieces can be radioactive for up to 25,000 years. And so you have to, it's not that big of a problem. You just bury it and stuff like that. But this is radioactive. None of this stuff is radioactive. Okay. So there's no radioactive waste in fusion reaction. Okay. Anyway, so this is a exothermic reaction. Okay, so isotopes of uranium. So these are the two main isotopes of uranium. There are other isotopes, uranium-235, okay, and uranium-238. Okay. Again, uranium-235 is 92 protons and 143 neutrons. And uranium-238 has 92 protons and 146 neutrons. It's just the heavier cousin. So naturally occurring, when you go mine uranium, 99.3% is uranium-238 and 0.7% is uranium-235. Okay, so to make fuel, you have to enrich it. Okay. Uranium and thorium are the only two naturally occurring elements. What are the naturally occurring elements? Everything in black is naturally occurring. Okay, and everything in the light white color, those are on man-made. Okay, thorium is 90, so 2 spots behind uranium. Okay. So uranium and thorium are the only two elements you can you can use in a nuclear reactor. Uranium is what all reactors are uranium reactors. Thorium you can use to make a fissile material. Okay? So you can use thorium to make nuclear fuel. All current reactors use uranium as fuel. Okay? Thorium itself is not fissile, but can be used to breed a fuel. And we'll come to that. Okay. So here's a slow neutron. What do we mean by slow neutron? How fast is it going, roughly?
2 kilometers.
Huh?
2 kilometers.
Very good. Okay, 2 kilometers a second. It'll get absorbed, and then it'll break up into two pieces. See, it broke up into this piece, which has 141 nucleons, broke up into this piece, which has 92 nucleons, and three neutrons are released on the average. Fission reaction represent the breakup of a nuclei into lighter components. Why is energy released?
Because the products weigh less.
These guys weigh less. Okay. Now, why do they weigh less?
Because their bond is strong.
Yep. So the number of neutrons and protons is the same here and here. Okay. So in these guys, the neutrons and protons are more tightly bound. And the more tightly bound you are, the less you weigh on the average. And since you weigh less, that missing mass is what got converted to energy. Okay? So here's a multi-million-dollar graph that shows you that. Okay? So in uranium-235, that is the binding energy. The binding energy is 8, this is in units of MeV, it's 8 MeV. What that means is each neutron, okay, so the neutron's weight is about 1,000 MeV in these units. Okay? When they say the weight, it's E equal to mc square. This is units of energy. So a neutron weighs 1,000 MeV. Okay? A neutron and a proton weigh the same. In a uranium nucleus, the binding energy is 8 MeV. That means it weighs 8 MeV less. So what is the mass of a neutron in a uranium nucleus?
993.
2. Okay? So in a uranium nucleus, a neutron weighs 992 MeV. What you did was you broke this up into two little pieces. Okay? Here is barium. Let's say in barium, the binding energy is 9 MeV. So in barium, how much does a neutron weigh?
991.
991. You're learning the secrets of nuclear energy. Okay, each of those guys weighs less. Okay, and that is what's released. Okay. So you want to make a product that is more strongly bound, so you can release that energy. Okay. Same thing is happening here, except that in the other direction. This is a fusion reaction. Again, this is less tightly bound. This is more tightly bound. These guys weigh less in there. Okay, and that's what this graph is showing. You can go in the other way. So this is this is less tightly bound, and as you're going to a heavier nucleus, you're more tightly bound, and that is releasing energy. Okay. So this is the binding energy curve. What that binding energy means is, let's say if you want to pluck a neutron out of a uranium nucleus, you would have to put in that much energy to pluck a neutron out. Okay? So that's how strongly it's bound. All right, neutron and motion are the starting point of everything that happens in a nuclear reactor. When a neutron passes near a heavy nucleus, for example, uranium-235, the neutron may be captured by the nucleus, In certain cases, the initial capture is followed by fission. It might spit it out, but that is generally followed by fission. Whether capture and fission take place depend on the velocity of the passing neutrons. Okay. So if you have a very fast neutron going by, the probability of it causing fission is lower. Okay. Fission may take place in any heavy nuclei after neutron capture. Low energy thermal neutrons meaning their temperature is roughly room temperature. Okay. When something is hot, things are moving fast. Okay. So thermal neutrons are room temperature neutrons, you can think of them. Cause fission in isotopes of uranium and plutonium. So uranium is nuclear, naturally occurring. Plutonium is, what is plutonium? 94. It has 94 protons. That is a fuel made in nuclear reactors. Okay. This just tells you about odd numbers, don't worry about it. Okay. In nuclei containing an even number of neutrons, fission can only occur if the incident neutrons have energy greater than 1 million. Okay. Okay, fission of isotopes of uranium whose nuclei contain odd number of neutrons. So uranium, these guys that have odd number of neutrons, this guy has 143 neutrons, this guy has 147 neutrons, and this guy has 141 neutrons. This is the guy that's made out of thorium. Okay, so this guy is fissile as well. He's not naturally occurring enough. Okay. This guy is what we use in all reactors, and this guy also can be used in nuclear reactors. Newly created fission neutrons are in this category, and their speed is about 7% of the speed of light. When you split uranium nucleus, these guys are going extremely fast, about 20,000 kilometers a second. And the probability of them causing a further reaction is small, so you have to slow them down. Okay, they're going at 7% the speed of light. A neutron is said to have thermal energy when it's slowed down to be in thermal equilibrium with the surrounding. Okay, so the neutron has to be slowed down tremendously, from 20,000 kilometers a second to 2 kilometers a second. So most reactors using U-235 fuel need thermal neutrons. Why do they need thermal neutrons?
So it slows down, slows down.
So the probability of it causing a further reaction is 100 times greater. Okay. And a moderator such as water slows down fission reaction, neutrons. Okay. So that's what a moderator does. So U-235, a naturally occurring isotope, is only 0.72%, and so you have to enrich it. These guys are called fertile isotopes. What do you think it means when they're fertile isotopes? You can use this, it's like fertility of an animal. It can produce more progeny. Okay. These guys can be used to produce fuel. Okay. So they can be converted into nuclear fuel. They themselves are not fuel. Neutron released in fission initially are going at 20,000 kilometers a second, and you have to reduce its speed to, okay. So in energy units, it's about 1 MeV. You got to slow them down to 2 kilometers a second. In energy units, you need to slow them down to 0.02 eV. Okay. So a moderator does that. A moderator material comprising of light atoms. Okay. In a reactor using natural uranium, so what is the problem with using natural uranium? What are you splitting? You're splitting uranium-235, and so your target molecules are much rarer. when you enrich them, there are more uranium-235 for you to split. Okay? So, in a natural unrich uranium, the only suitable moderators are graphite and heavy water. With enriched uranium, ordinary water may be used as moderator. Okay, and so this is if you can use ordinary water, that's cheaper. So you spend your money enriching the fuel. Do you remember how enriched the fuel was at the UF reactor?
Wasn't it low?
Huh?
They switched from high to low.
Yeah. So what was it?
Like, I wanna say 1%.
It was 20% enriched. Okay. So there's a nuclear reactor at UF, and so naturally occurring, the uranium-235 is 0.7%. So in the reactor at UF, the amount of uranium-235 is 20%. Okay? Water is also commonly used as a coolant to remove heat from the heat and generate steam. Okay. All right, so here's the process. There's a neutron. You shoot it at a uranium-235. This is in an excited state, and pretty soon it'll split into two pieces, okay, and 3 neutrons. When a neutron is captured, the energy of the neutron is distributed among 236 nucleons in the compound nucleus. Okay. When it's absorbed, it's strongly bound, and about 8 MeV of energy is produced. Remember, its weight reduced from 1,000 MeV to 992 MeV. So 8 MeV of energy is released. Okay, so that energy is distributed among the 236 nucleons. This nucleus is unstable. This is unstable and breaks up into 2 fragments of roughly equal masses. The fission process is followed by an emission of about 2.45 neutrons on the average. Okay, so some fission will release 2 neutrons, some will release 3, and so on. These neutrons can cause further reaction, making a chain reaction possible. About 85% of the energy released is in kinetic energy of the fission fragments. 85% of the energy released. How much energy is released? 200 MeV. That's in the kinetic energy of these guys. So these guys are moving fast. That's in the heat. A small fraction of the energy comes from gamma rays. So these guys are excited and they'll release gamma rays. Yeah. About 6% of the heat generated in the reactor core originates from radioactive decay of fission products and transuranic elements formed by neutron capture. Okay, so here is a safety concern. Even after you shut off a nuclear reactor, if it has been running for a while, these products are radioactive. And so they're still producing quite a bit of heat. And if you don't have a mechanism for removing this heat, then it can cause problems. Okay. If there's water surrounding the core, and if you're not removing the heat, eventually the water will heat up too much and water will split. And this fella is explosive. So if it blows up the container, then radioactivity will leak. So that's what causes most of the accident. So how do you make it safe, a reactor?
Enough coolants?
Hmm?
Enough coolants?
Don't use water for a coolant.
Oh. So the graphite will do?
They use salt, molten salt.
Salt.
Yep. They use gases now. Gases won't explode.
Oh, like normal gases? Or
I'm sorry?
Like normal gases?
Yeah, something like that. So here's a. So you see, here's a pebble bed reactor. This is a new design, a new reactor design that attempts to deal with safety issues. Is a pebble bed reactor. So these are fuel pellets, and these guys won't melt. Okay, and you see the uh, the cooling is a gas. Okay, and then what you do is you take water, and this water absorbs the heat from there, and then this steam is generated. Okay, steam which is turning the turbine, which is turning the generator. Okay, if something goes bad, just stop pumping water in, and this is safe. Okay, the gas can heat all at once. Okay, and it'll be so. This is a much safer design. Okay. So about 6% of the heat originates from decay. This must be allowed for when the reactor is shut down, so you should account for that. Since heat generation continues after fission stops, radioactive decay of used fuel generates heat and hence needs cooling. In the Fukushima accident, when cooling was lost, why was cooling lost? So Fukushima happened in 2011. Do you guys know what caused it?
Not Fukushima's.
I'm sorry?
Not Fukushima's. I don't know much about that one. I just know.
Yeah.
A
So
tsunami, wasn't it?
yeah,
It broke
so
it?
tsunami caused it. So all power went down. Okay, and so the cooling water pumps stopped. Yeah. The radioactive decay of used fuel generates heat and hence needed cooling. In Fukushima accident, when cooling was lost an hour after shutdown, this used fuel was still producing about 1.5% of the full power, leading to an explosion. Even after 1 year, typical used fuel generates about 10 kilowatts of decay heat per ton. Okay, decreasing to 1 kilowatt per ton after 10 years. So you have to account for the heat. Okay. Yeah. All right, so delayed neutrons. So we'll talk about two more slides and then we'll stop. Okay. Following fission, okay, so here is the fission reaction. Here are the fission products. Following fission, 99% of the neutrons, 99% of these neutrons are emitted immediately. Okay. They're emitted because these guys had too many neutrons and they're unstable, so they'll spit out a neutron. Okay. Most of them are emitted immediately. If all of these guys were emitted immediately, if 100% were emitted immediately, then you couldn't make a nuclear reactor. Okay, all you could do is make bombs. So this is crucial. Okay, so for 99% are emitted immediately, called prompt neutrons, but a small portion are delayed. About 1% are delayed by, on the average, 10 seconds. Okay. And that is what enables you to pull out control rods slowly enough to make a nuclear reactor critical. Okay. So the delayed neutrons come from radioactive decay of certain fission products. Okay. So they're not spitting out the neutrons immediately. The longest delayed neutron group has a half-life of 56 seconds. So the slowest release is about 56 seconds on the average. Delayed neutrons are a crucial factor enabling chain reaction systems or reactor to be controllable and to be held precisely critical. So if you didn't have delayed neutrons, you couldn't make sure that one caused further reaction. Okay? So fission of uranium-235 nuclei typically releases 2 or 3 neutrons with average of 2.5. One of these neutrons is needed to sustain a reaction. The others leak from the core region or are absorbed in non-fission reactions. Okay. Neutron absorbing control rods are used to adjust power output of the reactor. Okay. So okay, when you want to produce maximum power, you lift all control rods. When you want to produce half as much power, you put half the control rods in. Okay, and only reaction over here is going on. Okay, so that's how you adjust power. If you the power output. Okay, so control rods are used to adjust the power output of a reactor. So control rods are made out of boron or cadmium. Both are strong neutron absorbers and inserted among the fuel assembly. So you want a material that is neutron absorber, and boron and cadmium are the two. So boron is number 13. So on the second row, B5. Okay, that's boron. And cadmium, where is cadmium? Cadmium is 48. Yeah. Okay, so here's fission energy. Energy released in a fission of a nucleus depends on its precise breakup, but on the average 200 MeV of energy is released. When you split uranium-235, you release 200 MeV of energy. Okay. In contrast with 4 eV per atom of carbon burned in fossil fuels. Okay. So 200 MeV versus 4 eV. 200 MeV is 200 million eV. So you're releasing 50 million times more energy than when you burn one carbon atom. Hence, when you split one uranium nucleus, you get 50 million times the energy you get from burning one carbon atom. So that is the lure of nuclear energy. And the biggest thing is you're not releasing carbon dioxide. All right. So we'll stop.